Hello, welcome back to Quest 0. In today's session, we're going to see how to solve a problem, a beam problem, especially using the Rayleigh Ritz method. We have seen until now the different numerical involving bars. So from this particular solution, for this particular numerical or problem, let us see how to obtain the maximum deflection at the point of application of load. So the statement goes as, using Rayleigh Ritz method, find maximum deflection of a simply supported beam of length L subjected to a point load capital P at the center. So this is capital P and it is causing deflection Y max at the center. The overall length of the beam is capital L. Okay. So what we'll do for this numerical is, we will obtain the solutions using both polynomial and trigonometrical, and we will see which approximation works better. Okay. So the very first thing that we are going to do is, first step is to obtain the potential energy functional. So in order to obtain the potential energy functional, we need to obtain the strain energy and work potential. Potential energy functional. Phi is given by strain energy plus work potential. For beam, strain energy is given by EI by 2 integral over the length dou square U by dou x square whole square into du dx. Work potential is given by, you have the load which is acting on the body in SP, and it causes a displacement of Y max. This is the work potential. Therefore, pi will be equal to EI by 2 0 to L dou square U by dou x square whole square dx minus P Y max. Okay. So this is the potential energy functional. Now the second step is to assume the polynomial or trigonometric approximate displacement function. So I'll call this as equation 1. The potential energy functional equation, I'll call this as 1. Now for beams, let the approximate displacement function be approximate displacement function B. For beams, it is always better to assume a trigonometric function. So in this particular case, I'll assume the trigonometric function first for the displacement, and I'll compare the solution that we obtain with an assumption made with the polynomial function. So let us assume the trigonometric function initially. So u is equal to a sine pi x by L. Let me not go with further, okay, because the result will improve, but my computational time will also be increased. Hence, I'll assume only the very first term in the trigonometric series. So, a sine pi x by L. So, I'll call this as equation 2. This particular trigonometric function should satisfy the boundary conditions. So, what are the boundary conditions? Applying boundary conditions, applying the boundary conditions to this at x equals 0, displacement u is equal to 0. So if you apply these boundary conditions, and also we'll take up the next boundary condition as well, does it satisfy? When x becomes 0, it is sine 0, which is 0, u is 0, so it satisfies. And at x equals L, u is equals to 0. At x equals L, u is equal to 0. So when x becomes L, sine pi is 0. So a0 is equal to 0, which is equal to u. So both the boundary conditions are satisfied by the assumed approximating displacement function. So the assumed displacement function, function satisfies the boundary conditions. Now at x equals L by 2, u is equal to, at x equals L by 2, where the point load is acting, u is equal to y max, which is the maximum deflection. So therefore equation 2 becomes, y max is equal to a sine pi into L by 2 divided by L. So this is nothing but a sine pi by 2, which is nothing but y max equals a. So this equation, let us call it as 3. Y max equals a is 3. Differentiating equation 3 twice, because we need to obtain dou square u by dou x square. Dou u by dou x is a cos pi x by L into pi by L. We are differentiating equation 2 twice. Dou square u by dou x square is minus a sine pi x by L pi by L whole square. I call this as equation 4. Once we have obtained the second order differential, we will substitute this same into equation 1. If you observe, now we had differentiated u twice with respect to x to obtain minus a sine pi x by L pi by L whole square. Now substituting this equation 4 and equation 3 in equation 1, which is the potential energy functional equation, will obtain pi as ei by 2 integral 0 to L minus a sine pi x by L pi by L whole square, the entire term square, dx minus p into a. So this becomes ei by 2 integral 0 to L a square pi by L to the power 4 sine square pi x by L dx minus pa. Okay. Now taking all the non-integral terms, ei by 2 a square pi by L to the power of 4 integral 0 to L sine square pi x by L dx minus pa. Now in order to integrate sine square pi x by L, we'll convert it to the form of cos, which is nothing but ei by 2 a square pi by L to the power 4 integral 0 to L 1 by 2 1 minus cos 2 pi x by L. We'll convert it into this form and proceed further with the integration. So this becomes ei by 4 a square pi by L to the power of 4. So integral of, there is no term present, so it will be x minus integral of cos 2 pi x by L is sine 2 pi x by L divided by pi 2 pi L, and the limits from 0 to L minus pa. So this becomes, if you simplify this, it will be ei by 4 a square pi by L to the power of 4. This becomes, if you substitute the upper limit, it will be L minus 0, and when you substitute 0 also it is 0, so L minus pa. This is the potential energy functional. Minimizing this potential energy functional, which is the last step, minimizing the potential energy functional we obtain dou pi, the variable is only a, dou a should be equal to 0. So this becomes dou pi by dou a is equals to ei, this becomes 2a by 4 is 2, ei a by 2 pi by L to the power of 4 L minus P. and this is equal to 0. So this becomes a into ei by 2 pi to the power of 4 by L cube is equals to P, or A will take a value of P L cube or 2P L cube by EI pi to the power of 4. So maximum deflection is given by Y max, and it is equal to A is nothing but 2PL cube by pi to the power of 4 EI. If you substitute the pi value and simplify it with 2, you will obtain Y max as PL cube by 48.70 EI, which is very close to the exact solution, which is 48 EI. Okay. Now we'll look at the possibility of using an polynomial displacement function. So let us assume the polynomial displacement function. So let the approximate displacement function be u equals a0 plus a1x plus, since the potential energy functional has the second order differential term dou square u by dou x square, the polynomial should be of second degree. So a1x plus a2x square. If we limit ourselves to the first order polynomial, when we try to obtain dou square u by dou x square, we will not be able to satisfy the condition. So I'll call this as equation 2, and the boundary conditions are at x equals 0, u is equal to 0. So substituting this into equation 2, we obtain a0 as 0. So equation 2 now becomes u equals a1x plus a2x square. The second boundary condition is at x equals L, u is equal to 0. So substituting this, we obtain 0 equals a1 into L plus a2 L square, which is nothing but a1 will take a value of a2 L. Substituting this into equation of u, will obtain u equals minus a2 L plus a2 L x plus a2 x square. Now we need to obtain two things from our approximation. The first is to substitute y max, where the load is being acted, what is the displacement that we need to calculate, and the second order differential of the assumed displacement function. So we'll differentiating twice the above equation, or let me call this as equation 4, differentiating twice the above equation, obtain dou u by dou x is minus a2 L plus 2a2 x dou square u by dou x square we obtain as 2a2. Okay. Now with this value that we have obtained, call this as equation 5, we need to obtain y max. So y max is, or the maximum displacement is at the center. At x is equals to L by 2, displacement u is y max. So substituting this into equation 4, we obtain y max is equal to minus a2 L into L by 2 plus a2 L by 2 whole square. This is nothing but minus a2 L square by 2 plus a2 L square by 4, or when you simplify this, y max is equal to minus a2 L square by 4. Call this as equation 6. Substituting values from equation 5 and 6 in equation 1, which is the potential energy functional, which we had done very first. 5 will be equal to ei by 2 integral 0 to L. It is dou square u by dou x square, which is 2a2 whole square into dx minus p into y max. Y max is minus a2 L square by 4. And this is nothing but ei by 2 4 a2 square integral 0 to L dx minus into minus plus p a2 L square by 4. When you integrate the term, you get ei by 2 4 a2 square x from limit 0 to L plus p a2 L square by 4. Applying the limits, ei by or 2 ei a2 square into L plus p a2 L square by 4. This is the potential energy pi. The next step is to minimize the potential energy functional. Minimizing the potential energy functional, dou pi by the variable that is present is a2. Dou pi by dou a2 should be equal to 0. So dou pi by dou a2, if you do it, it will be ei L into 2 a2 plus p L square by 4 is equal to 0. So now this will be 4 ei L a2 is equal to minus pl square by 4, or a2 will take a value minus p L square or PL divided by 4 into 4 is 16 EI. This is the value of A2. So therefore, maximum displacement Y max is equal to, what is the value of Y max that we have obtained? It is minus A2 L square by 4. So minus Y max is minus A2 L square by 4. Substituting the value of A2, so minus of minus PL by 16 EI into L square by 4 will give us PL cube by 64 EI. If you observe, this is far off from the exact solution. Hence, for beam, assuming trigonometric displacement functions yields better results. Thank you for watching. The next sessions will take up one more problem on simply supported beam, and then we'll move on to cantilever beam. Thank you.